Welcome students. In today's class, what we are going to do is we are going to use fundamental solution. So what is so special? Okay. So the speciality, let me put it this way, the speciality of fundamental solution is it helps us to solve Poisson equation. Okay. So non-homogeneous. So see, fundamental solution essentially deals with a homogeneous problem, right? Laplace equation, Laplace equals 0. But what we are saying is we can use that particular function from the solution of a homogeneous problem in Rn minus 0 and use it to solve something which is like an inhomogeneous problem. So how to do that? Yeah, let's see. So motivation. Now you see what happens is this. Let's say x going to phi of x. Yeah, this is harmonic for x not equals to 0, yes or no? Yeah, because we have seen that phi solves this problem, yeah, for all x in Rn except at 0. So basically this is a harmonic for x not equals to 0. Yeah, if this happens, you just shift the origin to y. Here the origin is at 0. So you just shift it to y. What happens is, therefore, x going to phi of y minus x, yeah, or x minus y is harmonic for x not equals to y. Yeah, I can do this thing. Why? Because essentially harmonic functions are translation invariant, right? Yeah, we talked about it earlier. Laplace equations are rotation and translation invariants. Okay, so basically if you translate the function, it is going to be harmonic. It's not a problem. Yeah, so if that happens, then for a nice, yeah, it's not very mathematical, but let me write it like this: f from Rn to R. F from Rn to R, yeah, the map x going to phi of x minus y, f of y, yeah. So this is not x not equals to y, of course, is harmonic for each y in Rn, yes. Yeah, it is of course harmonic. So if you fix a y in Rn, this is going to be harmonic. Yeah, why? Because you see, when you fix a y in Rn, f of y, f is some function at the point y, it is taking some real value. So basically, you are essentially multiplying it by a constant, yes or no? See, this function is a function of x. X is going to this thing. It's a function of x. As a function of x, this is harmonic. It's not a harmonic with respect to y. You do understand what I'm saying? See, x going to phi of x minus y is harmonic. Yeah, it is harmonic as a function of x. Yeah. Again, here when I'm multiplying it by f of y, for a fixed y, f of y is just a constant essentially. So I'm multiplying it by a constant. It's a function of x. Yeah, and so it remains harmonic. It's not a problem, because you see, if Laplacian of u equals to 0, Laplacian of c times u, let's say, will it be 0? Of course, because it is a linear function, right? So this is 0. So this c here is f of y. Now y may change, and that does not matter. I mean, it's going to be the same thing. Yeah. So essentially, what is happening is we are saying that this kind of function has to be harmonic, right? Now, if it is harmonic, then you see, then there is a reasoning. So we can say that, let's say, if you just integrate it over Rn, okay? So integrate over Rn, okay? Phi of x minus y, okay? F of y dy, f of y dy, this particular thing, this should solve, therefore this should solve the Laplace equation, yes, okay. You understand what I'm saying? See, for every x it is harmonic, right? So if for every x this solves the Laplace equation. So basically, if I am taking the integration on Rn, yeah, and let's say if I am defining ux to be that particular thing, it's a new function ux. Yeah, this is I am defining it like this. Then I can say that this solves the Laplace equation u. Yeah, but the problem is it doesn't. Yeah, but it does not. Does not. Yeah, but it does not. Now, what is the problem? The problem is, see, let's say if Laplacian of u, if you just write it like this, I mean, if you take the, Laplacian inside of this thing, it will be delta x of phi of x minus y f of y dy, right? It should be something like this, and delta x of f of x minus y is 0, so it has to be 0. So it, I mean, a priori it seems to solve the Laplace equation, okay, but it does not. Why it does not? Because you see this particular function, okay, because it does not. Yeah, I should have wrote it here. Since you see the second derivative of phi at the point x minus y, yeah, this is not summable near x equals to y. Is this clear? See, there is a singularity at x equals to y. This phi blows up, right? So d2 of phi, that is not integrable. Summable, whenever I say summable, I mean integrable. Integrable, clear? Yeah, it is not integrable near x equals to y, and hence and therefore the differentiation under the sign of integration, differentiation under the sign of integration is not valid. Clear? Then it is not valid. That's what. Okay. So what happens now? So what we are going to do is this. See, so this is a theorem. We start with this. We start by assumption on f. So essentially, I said nice f. Huh? What is nice? Let's see. So we start with f, which is c infinity, or you can take c2. I mean, it's not a problem. Let's say c2. Yeah, and with a compact support in Rn. Clear? Okay. So twice differentiable with compact support. Twice differentiable with compact support. Compact support. Okay. So once I start with this f, then there is the theorem which I want to solve. Yeah. So the theorem says that define u of x. Yeah. You define it like integral over like this. Yeah. Integral over Rn phi of x minus y f of y dy. You define it like this. Okay. Where phi is the fundamental solution. Okay. Fundamental solution. Okay. Where phi is a fundamental solution. Okay. Then number A, u, which you get u. Yeah. It is C2 of Rn. Okay. See, if you are defining it like this, phi is not, the twice derivative, this has a singularity at x equals to y. Yeah. But still, it is saying that if you define it u of x like this, then you have to be C2 of Rn. Yeah. Moreover, u solves. Yeah. See, we were trying to make u to solve this equation, Laplacian u equals to x. Actually, what happens is you solve this equation, the Poisson equation. Okay. In Rn. Is this clear? Yeah. So basically, we were thinking that it should solve the Laplace equation, but in reality, it solves the Poisson equation. And we'll see later on that this actually can be useful to provide a formula for the solution. Okay. So we'll look at it later. We'll revisit this particular thing later. Okay. So first of all, what we are going to do is we are going to start with the proof of this thing. Proof one. So before I start with the proof of this thing, let me give you a small, it's not a remark, but let me give you a suggestion. Yeah, the calculations which I am going to do. So this is you should be very familiar with this sort of estimate. So we are basically going to do some estimates. Yeah, please understand this thing in PDEs, the research problems. Yeah. If you do theoretical PDs, these are the type of things which you need to do. Yeah, and you should be quite, this should be bread and butter for you. So essentially, this is going to be a little, dry at first, but I mean, you will get the hang of it if you give enough time. Okay. So first of all, let's say we start with U of X. So again, whatever I am doing, please do it yourself. Check once. Okay. I mean, without that, you are never going to understand. I mean, I can just do it here. It does not matter. Huh? Please, I mean, you can just look at the calculation. That's not a problem. But do it yourself. Yeah, that's the important thing. So, first of all, Ux is given by phi of x minus y f of I dy over Rn, right? Now, I am just doing a change of variable. This I don't think I have to show you. You guys can do it yourself. Just a change of variable. Phi of x minus y f of I dy is getting changed to phi of y f of x minus y dy, right? Okay. This is just a change of variable. So, change of variable. Clear? Okay. Now, therefore, I want to show u is in C2, right? So, first of all, let's show u of xy exists. The first derivative of u. Okay. The partial derivative of u with respect to any xy. So, what is it? It is u of x plus h ei minus u of x by h. Clear? So what is it? This is integral over Rn phi of y. Clear? Okay. F of x plus h ei. Okay. Minus y minus f of x minus y by h dy. Right? I can do it like this. Yeah. See, what is the idea behind this change of variable? If I'm not doing this change of variable, I have to do all of this in phi. I don't want to do that in phi. Why I don't want to do that in phi? Because phi has a singularity at x equals to y. Yeah, I want to avoid that. So I just replaced it by phi of y. Yeah, so the singularity is getting replaced at y equals to 0. And after that, since this is all happening with respect to f, I am just putting everything on f and I'm working with it because f is C2. We know that. Yeah, we know that f is C2. We have assumed, if you remember, we have assumed f is CC2. So C2 with a compact support. Okay, right. So and what is EI? Sorry, EI is 0, 0. This is just 1, 0. Yeah. So ith coordinate it is 1. Okay. So basically, it's just the ith unit vector. Yeah. Now, you see, f is C2, right? So, f of x plus h ei minus y minus f of x minus y by h. What happens to that? Yeah, this goes to f xi at the point x minus y. I think you agree with me here. Yeah, this is uniformly, right? Uniformly. Yeah. So, whenever I write uniformly, I will just write it like this. This goes uniformly as h tends to 0. Yeah, I think you will agree with me here. Why? Because f is C2. C2 of Rn. It means that it is twice differentiable. So basically it is once differentiable. If it is twice differentiable, it is definitely once differentiable. If it is once differentiable, it means that gradient of f, yeah, exists and is continuous, right? Exists and is continuous. Yeah. And what is gradient of f? Gradient of f is f x1 f xn. Clear? Okay. So this particular each component exists and is continuous if f of xi. So let's say f of xi exists and is continuous. What does that mean? It means that this particular thing converges to this. This is just a definition of f of xy, right? Okay. So this converges uniformly, and hence, and thus what happens? U of xi at the point x, this will be given by integral over Rn, okay, phi of y del f del xi at the point x minus y dy. This is for I equals to 1 to n. Clear? Yeah, I can write it. Why? Because I'm just, you see, uxi, if I'm just taking limit h tends to 0 on both sides of this thing, yeah, I can take the limit inside h tends to 0 because, I mean, the integration is with respect to y, so there is nothing to worry about. I can take this inside. If I take this inside, this particular thing converges to u, yeah. So, uxi is basically integral over Rn phi of y del f del xi x minus y dy. Yeah, and similarly you can also take another derivative here uxi xi. Yeah, now you think of uxi as some phi and do the exact same thing. Yeah, so what will happen? It will be phi of y, the fundamental solution, del square f del xi. Let's do it like j. Yeah, del xj. I mean, it does not matter. I mean, for now, but okay. So this is I, j is between 1 to n. Clear? Yeah. So this expression I am taking again with respect to xj. I am doing exactly the same thing which I did. See, f is c2. So the same kind of argument works on the gradient of the partial derivative of f with respect to xi. Yeah. And that will give you d2f dxi dxj. Right. So that is your uxi xj. So what does that say? See, this expression on the right hand side, yeah, this is continuous with respect to y. Yes or no? You do understand what I'm trying to say. This is a continuous, this expression, yeah, this is continuous with respect to x. Please remember, this is continuous with, see, here there is a singularity with respect to y, yeah, but I don't care because this is with respect to x. This is a continuous function with respect to x, yeah, and so what we can say is, and u is a function which is a function of x. So essentially, therefore, I can say that u is in C2 of Rn. Clear? Okay. Right. Now, the second part, yeah, and this is the difficult part actually to prove. Yeah. So please, I mean, stay with me. You have to show minus Laplacian u equals to f in Rn. Huh? Okay. So how to show this? The part 2. So to show minus Laplacian of u equals to f in Rn. Okay. How do we show that? See, please remember that phi blows up near y equals to 0. Right? Phi blows up near y equals to 0. So what we are going to do is we are going to break Rn into two parts. Yeah. One part is we'll take a ball of radius, center at origin and radius epsilon, and outside the ball, we'll take this integral in two parts. Okay. So from here, what do you get? Laplacian of u of x is given by integral Rn. I'll just break it up. B0 epsilon phi of y delta x of f of x minus y dy. Okay, why I am writing delta x? See, there are two variables x and y, so it makes sense to write what is this. The Laplacian is with respect to which variable? So here it is with respect to x variable, right? So delta x of x minus y. If I'm taking the sum, it will be sum, right? So if you take the sum of this thing over I equals to j from 1 to n, then it becomes this, right? And again, it is in Rn. I am taking breaking up into two parts. One is ball with 0 epsilon and one is Rn minus B0 epsilon. Okay, and you have phi of y delta x of f of x minus y dy. Clear? Okay. Now, once I have this thing, I will just write it like this: I epsilon plus j epsilon. Clear? Two parts. This is I epsilon, this is j epsilon. Yeah, this is what I am writing. So now let's do what I epsilon is. I epsilon. So mod I epsilon. Yeah, this is what? This is integral B0 epsilon phi of y delta x of x minus y dy. Yeah, this is there. See here, this particular expression, f is in C2. So delta x, Yeah, delta, see, delta, what is the relation between D2 and delta? Relation between D2 and delta. If you are confused here, D2 in two variables, just think it is UXX, UXY, UYX, UYY. And what is delta? Delta is just the sum of these two. So basically, delta is trace of D2. Clear? Trace of D2. So essentially here also this delta is just some coefficients of D2, right? Your sum of some coefficients. Since f is C2, this particular thing has a bound on the, so this is a ball, right? So it's a bounded set. Yeah. So it's a, now f is C2, it means the double derivative exists and it is continuous. So all the partial double derivatives, mixed derivatives exist and they are continuous. So delta x of f is continuous function on this ball. I can take the maximum and I can put it outside. Okay. So let's take that and get it outside. So this is less than equal d2f. I'm taking the maximum of this thing, L infinity of Rn. Yeah. For some of you who know some measure theory, you guys will understand what I'm trying to write here. But for others, let me give you this. So let's say f, yeah, f is a continuous function on a bounded set. Let's say, yeah, L infinity of Rn. If I'm just writing it like this is basically the maximum of mod f, okay, over Rn. Okay, Rn can be changed to some omega. So L infinity Rn is maximum of f. Whenever I'm writing the norm of L infinity norm, it means I'm just taking the supremum, the maximum norm. Here the maximum exists. Please remember, the f is in Rn. It does not matter. See, f is in Rn, but the maximum exists because f is in Cc. There is a compact support, right? That is why the maximum is attained, and hence I can write. Otherwise, you just write it as supremum. Okay, just think of it like this. So this is, I take the maximum of d2f and put it outside. Now I am only left out with phi of y dy over p0 epsilon. Okay, mod of this thing. Now see, let's do this part. b0 epsilon phi of y dy. Okay, so this is b0 epsilon. Okay, let's do it for n greater than 3. So for n greater than equal 3, n equals to 2, I want you guys to check yourself. So this is what it is, 1 by n alpha n minus 2 is there, no? I forgot to write it, n minus 2. 1, yeah, if you remember, please check what is phi of y. Let's check this part. What is phi of y? Yeah, 1 by n minus 2 alpha n, 1 by mod x small power n minus 2. If you remember this alpha n, yeah, I did not write this alpha n is the volume of the unit ball in Rn. Unit ball in Rn. Clear? Okay. So for all of you guys who understand measure theory, this is just a measure of the unit ball. Yeah. So n minus 2, 1 by mod x to the power mod y to the power n minus 2, okay, dy. This should be the case. So let's you see this is basically a constant dependent on n. Throw it outside. So this is some Cn. I will write it like some Cn. Yeah, I'm not really interested in that thing. b0 epsilon dy by mod y to the power n minus 2. Now you remember your integration on radial function. So by integration of radial function formulas, radial function, what do you get? We get that this particular integral dy but mod y whole power n minus 2 over b0 epsilon, yeah, can be written like this: 0 to epsilon, yeah, del b 0 r, yeah, dr by r power n minus 2. Sorry, I should write it like this: 1 by r power n minus 2, okay, and d Xi is there. Okay. No, it should be dr. No, it should be. So essentially, what I'm doing is this. See, first of all, I'm integrating this thing on the unit ball. Okay, integrating this thing on the unit ball. On the unit ball, yeah, this is a radial function. So basically, this is constant. So essentially, what am I going to get? So let me write it properly. So essentially, what I'm going to get is from here 1 by r to the power n minus 2. Okay, and then the volume of the there'll be 0 epsilon. Yeah, that is r to the power n minus 1 dr. Yeah, from there r to the power n minus 1 dr. Of course, our constants is there. Yeah, but I'm not writing all that. I mean, that is there. So if I calculate this thing, it is basically 0 to epsilon. Yeah, see, this is up to a constant. Yeah, this equals to is up to a constant. Okay. So 0 to epsilon 1 by r power n minus 2 to the power r minus n minus 1 dr. Yeah, this is just an integration with respect to radial function. See, what am I doing here is this. I want to integrate it over this particular ball. So I integrate it over this, just the boundary of the ball. On the boundary, this function. So let's say this boundary is of radius r. Yeah, this is the boundary of a ball with radius r. So if that happens, on that boundary, this particular thing is 1 by r power n minus 2, right? And after that, what happens is you are just integrating it between 0 to epsilon. You are just taking r to r from 0 to epsilon. Yeah. So this is why it is coming. So 1 by r power n minus 2 r to the power n minus 1. This is the volume of the ball. This particular, sorry, the surface area of this ball inside. Okay. So that is why r power n minus 1. Now it gets cancelled out and it becomes r dr. So this is r square. Yeah, it becomes r dr. Yeah. So this is up to a constant. Yeah, please remember this is up to a constant. Up to a constant. Yeah, I'm not writing all that, up to a constant. Yeah, here also same thing. Yeah, up to a constant. So this is essentially this is epsilon square by 2. Okay. So see what is happening here is this. If I take the bound on this thing, if I write it, so I epsilon, mod I epsilon, therefore mod I epsilon, yeah, this is less than equal d2f, the L infinity norm of this, the maximum of d2f, d2f, L infinity of Rn. Again, why this happens? Because f has a compact support, right? So we can write it like this, and yeah, and you see the mod of the integral, and mod of the integral is less than equals to the integral of mod, right? So mod of the integral is less than equals to the integral of mod. Mod of integral f is less than equals to integral mod f. Yeah. So if you write it like this, then essentially that is what is mod of this? This is epsilon by 2 up to a constant. So essentially there is a constant which depends on n times epsilon square. By 2, again it is getting absorbed by the constant. See, here we are not really interested in these constants. Yeah, all we are interested in is getting some estimates. The constants are always there. Why? Because you see, now if you take epsilon towards 0, essentially this I epsilon is 0. This constant does not contribute anything. I mean, this half and there are other constants, right? These constants, all of these are getting absorbed in this C. Clear? Okay. So this C is there, and this particular expression d2f, the infinity norm, time f square, epsilon square. Now this is fixed, right? The maximum of f is fixed. So maximum of f is fixed. So essentially I epsilon is bounded by epsilon square. Now as epsilon is small enough, if you take epsilon small enough, what is going to happen? If you can actually say that the mod of I epsilon, this is small. So this goes to 0. Okay. Now please check the n equals to 2 case. Okay, please check the n equals to 2 case. Now for j epsilon, now let's do the j epsilon part. Yeah, this is given by integral over Rn minus b0 epsilon, okay, phi of y delta y of f of x minus y dy. Clear? This is the case. Now this is equals to minus integral Rn minus b0 epsilon. Okay. I'm doing integration by parts here. Integration by parts. Yeah, integration by parts. What is it? It is phi of y. It is d phi of y d y with respect to f of x minus y dy. Clear? Okay. Plus on the boundary del b 0 epsilon. Okay. Phi of y del f del gamma of x minus y ds y. Okay. So let us explain what we why we write it like this. See, integration by parts. As you know that when we do integration by parts, one derivative comes to this part with a negative sign. So negative sign, one derivative comes to this part. So this loses one derivative, this gains one derivative. Yeah. So that happens. Plus on the boundary, see what is the boundary of this domain? This domain is essentially, this is b0 epsilon, let's say. The domain is essentially this thing. Yeah. What is the boundary? The boundary is the shared common boundary with the ball. Okay. So that is why this boundary. What is gamma? Where gamma is the, generally we write unit outward normal to the domain, right? To the domain. The domain is here. Outward normal is this side. So basically this is the inward normal to the ball, right? You understand what I'm saying? See, generally this gamma is the outward normal to the domain. Yeah. The domain is outside, inside out actually. Yeah. So the outward normal is basically inside the ball. Yeah. So gamma is the inward normal to the ball b0 epsilon. Yes, this is the inward normal. Yeah. Okay. I hope this is clear. Yeah. The normal to the boundary of the ball b0 epsilon. Clear? Okay. Inward normal. Okay. Now let's write this particular thing as again, this is k epsilon and the next one is L epsilon. This is k epsilon, this is L epsilon. Okay. Now therefore mod L epsilon. Yeah. What is it? Let's check. Mod L epsilon, I am doing this part. Yeah. This is mod of del b 0 epsilon phi of y del f del gamma of x minus y ds y. Okay. This is less than equals to integral del b 0 epsilon, okay, mod phi of y and the derivative, the norm of del f by del gamma at the point x minus y ds y. Now you see what happens to this thing. F is C2 with a compact support. So definitely the first derivative is also continuous and it is bounded, yeah, on this ball. So essentially this is a compact set, right? I can take the maximum of this outside. So essentially this is, I can just write it as df L infinity of, if you want you can just write it like Rn only, yeah, no problem. The maximum of f del f on Rn I can just say. See why this works, because you see, if you remember, f has a compact support. F is twice continuously differentiable, so it is once continuously differentiable, and the first derivative is also continuous. It is once differentiable and the first derivative is also continuous, because the second derivative is continuous. So the first derivative has to exist and it is continuous. Yeah. So if the first derivative is continuous, yeah, this is the compact set. There is a maxima which is attained. Yeah, that maxima is of course always less than equals to the maxima of f over whole Rn. You are taking the the maxima over any unit ball like this, the boundary of a unit ball is always dominated by the maximum over whole Rn. Of course it is, yeah, because this is a very big set. Yeah, so I'm just doing it like that, and then I have integral over del b 0 epsilon phi of y mod phi of y ds y. Okay. So if I write it like this, yeah, what happens here? So you see, phi of y is radial function on this ball, boundary of the ball. What did I say? Radial functions on the boundary, it becomes constant, right? So it is essentially, what is phi of y? So for n equals to, again, the n equals to 2 case, you guys have to do it yourself, yeah? Del b 0 epsilon mod phi of y dsy. Let's do that. Yeah, what happens to this? See, this is essentially del b 0 epsilon phi of y mod phi of y, some constant is there, yeah, some constant is there. I'm not writing all that constant, yeah, but here essentially it is 1 by mod y to the power n minus 2 dsy. Okay, see, on this ball, on del b 0 epsilon, this is essentially a constant, right? So this is c times 1 by epsilon power n minus 2, and then you have integral over del b 0 epsilon dsy, yeah, which is what? It is essentially the integral over the boundary of the ball, okay, the surface with respect to the surface, on the surface, yeah. So that will give you the surface area of the unit ball. So there is some constant again which is getting accommodated here, and that will give you epsilon power n minus 1. Is this clear? See, surface area of a unit ball is some constant times epsilon power, not unit ball, a ball with center epsilon is epsilon power n minus 1, yeah. So that is what it is getting outside. There is a less than equals to sign, sorry, yeah, I should write it like this, and I should actually, yeah, this is also less than equals to, there are some constants here, yeah, there are some constants here, you should write it like this, sorry, here there is no, here I just calculated this particular thing, yeah. So there is a constant, of course this is a constant, yeah, so all of that is, so this equality is up to a constant. Okay, you can write it like that, or you can just write a constant, yeah. Okay, so this happens, this is c pi times epsilon. So essentially what is happening here is you can bound mod L epsilon with C epsilon, yeah. So therefore, I mean, please check this part, mod L epsilon can be bounded by is less than equals to C epsilon mod log epsilon, okay. This is for n equals to 2, and C epsilon for n greater than equal 3. Please check this part, huh? And similarly, in the early part also, I forgot to write it here. I epsilon is less than equals to, of course, a constant times epsilon square if n is greater than equal 3. This we already saw. This is also a constant, right? I mean, there is nothing to write. And it is constant times epsilon square log epsilon, okay, if n equals to 2. So this part you have to check, okay. So here also this part you have to check, yes, okay. Once that is there, so L epsilon is bounded, I mean this is C epsilon, huh? As epsilon goes to 0, I mean this is very small, so I don't have to worry about all that. Now I have to worry about K epsilon. So what is K epsilon? K epsilon is integral Rn minus B0 epsilon, okay, delta phi of y f of x minus y dy minus integral del b0 epsilon del phi del gamma of x minus y f of x minus y ds of y, okay. So this is actually equals to minus del b 0 epsilon del phi by del gamma of x minus y f of minus y dy, right. See why this is happening, because here, see, this is the fundamental solution. This solves Laplacian of phi, solves the Laplace equation, yeah. Laplacian of phi is 0, delta phi is 0, yeah, for all x which is for all x not equal to 0. So essentially here y cannot attain 0 anywhere, right? So this is outside the ball. So Laplacian of p is 0, and in that case the whole thing is 0. Yeah. So in k epsilon I only have this particular expression to deal with. Now let's deal with this expression. So now what is gamma? Gamma is here, it is minus y by mod y. I hope all of you guys know this thing. Yeah. So see why this minus is there, because it is inward pointing normal. Inward pointing normal to del b. Okay. 0, 7. Yeah, that is why minus sign is there. And what is y by mod y? See, this is r by mod r essentially. Yeah, so you do realize, I mean, the unit normal is given by x by mod x. Yeah, not sorry, it's not r by mod r, it is x by mod x. Yeah, so that is always there, but since it is inverse, there is a minus sign. Okay, so gamma of y looks like minus y by mod y, and therefore del phi by del gamma of x minus y. What is it? This is gradient of phi at the point x minus y, yeah, dot gamma. What is gradient of phi at the point x minus y? So this you guys have to calculate yourself. Yeah, it is, let me write it down, it is 1 by n alpha n epsilon power n minus 1. This is on del b 0 epsilon. Yeah. Okay. See, phi of x minus y. Please remember, what is phi of x minus y? Phi of x minus y is 1 by n alpha n, okay, r power n minus, sorry, there is a n minus 2 is there, minus 2, r power n minus 1. It's not r, it is mod x minus y. Let me write it properly. 1 by x minus y whole power n minus 2, right? Sorry, n minus 1, n minus 1, n minus 2, yeah, sorry, n minus 2. You see, n minus 2, where is it? Mod x to the power n minus 2, right? Okay. So this is there. Now see, x and y, yeah, I am taking y on the boundary. Y, see, in this integral, y is on the boundary of the ball, yeah, and x is, I mean, x is not equal to y in that case, right? X is not equal to y, because since phi of x minus y will look like this, yeah. Therefore, if you take the derivative of this thing, d phi of y, so maybe I can just write it like this. Yeah, sorry, I made a mistake. Yeah, here it is fine, and then here it is phi of y. Yeah? This is the mistake I did. Sorry, this is the mistake which I did. So here and this also, here also. Sorry, one second. See, this is delta phi of y, right? So this is phi of y. This is why I couldn't understand. Yeah. So okay, this is fine. Yeah. Now, so in this case, you see, this is. Let me write it properly. Yeah. So let me write it like this. This is at the point y. This is y dot gamma. Okay. So this is y. Phi of y is equals to this times mod y to the power n minus 2. Okay, phi of y is this. Okay, in phi of y is this, you do realize that I can just take the derivative of this thing. Yeah, so d phi of y. Yeah, why I can do this thing? See, y is on the boundary. Y is on the boundary of this ball. Yeah, so definitely I can take the derivative here because y is not equal to 0. Yeah, it is on the boundary. It can never be 0. Yeah, so I can take this thing, and this is minus 1 by n alpha n. Okay, y by mod y whole power n. So please check this part. Yeah, please check this part. This is for y not equals to 0. See, y is on the boundary, so y cannot be 0, and hence I can take the derivative here. Yeah, because except at 0, everywhere it is very well defined. So I can just take the derivative and it becomes like this. Yeah. Okay. So once that is there, then What is K epsilon? K epsilon can be written as minus 1 by n alpha n epsilon power n minus 1. Okay, this one. Yeah, integral del b 0 epsilon. Okay, f of x minus y dsy. Clear? I can write it like this. See, this I just calculated, and after that del phi del gamma at the point y on the ball is given by this thing, right? It is given by this thing. Yeah, I just calculated I mean del phi del gamma, which is this. Why this is the case? Because gradient of phi, which is this. This is gradient of phi, right? Gradient of phi is this. And after that gamma is minus y by mod y. If I put it together on the ball, it is becoming 1 by n alpha n epsilon power n minus 1. Clear? Okay. So K epsilon, if you write it down, it becomes this, and this is equals to the average of del b x epsilon f of y ds y. Clear? Okay. What am I doing here? I just changed the variable. So I have just shifted the origin from 0 to x. Yeah, and so here the center is at x, and that is why this f becomes f of y. You just change a variable. Yeah. Okay. So, but you see, if you do the change of variable, the volume of the unit ball does not change. So essentially, this becomes this. This remains the same, and I'm just writing it like an average. Okay. So it becomes minus average of this. Now this goes to where? If you remember, minus f of x as epsilon tends to 0. Okay. Please remember, I am not using mean value theorem here, but this is actually true. I mean, this particular thing as epsilon tends to 0 is always true given f is continuous. Okay. So I mean, you can check that the average of over omega, let's say, okay, f of y dsy, this converges to f of, let's say, x is in omega. Yeah, x is in omega, which is center at omega, basically a ball. Omega is a ball and x is the center of the ball, so it becomes f of x, okay, as epsilon tends to 0. So this is omega is b x epsilon, let's say. Okay, you can show this thing that in the average of f over b x epsilon. Yeah, so let me write it properly. Yeah, del b x epsilon. Okay, so the average of f of y dsy goes to f of x. This is again in assignment. Yeah, please check. So this holds for any f is continuous. Continuous function, you can do this thing. Okay, once you do this, then k epsilon goes to minus fx. Now, if you put all of this together, yeah. So what is happening here? Let's check. Yeah, let's go back. So this is a long way. Okay, this particular expression, where is it? Yeah, this expression I epsilon on the ball, the whole thing is going to 0. We have checked that. Yeah, on the ball, you see I epsilon is going to a 0. So as epsilon to 0, this goes to 0. And this particular thing on Rn minus b0 epsilon, yeah, the first expression, you see, the first expression is L epsilon. Yeah, if you remember, yeah, the first, where is it? It's a big calculation once again. Yeah, so this is k epsilon plus L epsilon, right? L epsilon is n greater than equal 3. This is like C epsilon. As epsilon goes to 0, this particular expression L epsilon is very small, right? And the same holds for n equals to 2 also. And what about k epsilon? This k epsilon, this goes to minus f of x. Yeah. So hence u solves minus Laplacian of u equals to f in omega. Yeah. And hence you have the proof. So essentially what we did, so let me recall, quick recall. We wanted to solve the Poisson equation. For that we found out the fundamental solution, which is just a solution of the harmonic function in Rn minus 0. Use that thing, and we did something called a convolution. Okay, this is called a convolution which we did. This is called a convolution. We did the convolution, defined a ux, and we showed that this ux actually solves the Poisson equation. Given f is a nice function, f is Cc, f is a twice differentiable function with compact support. Yes, and we have showed that. So with this we are going to end today's lecture.